Bismillahirrahmanirrahim. Welcome to the lecture 7 memory management in an operating system. In this in this lecture we are going to discuss about the general concepts, then loading the programs into the memory. In that we are going to discuss about the address binding, then logical and physical address, memory allocation technique, paging and segmentation. So before we go into the memory management concept, let us discuss the basics of the memory devices. So the image what you see on the screen are the devices, memory devices arranged in an hierarchy. So here at the bottom, hard disk is there. At the top, we have this cache storage. So the cache storage, as far as the storage capacity is concerned, is less. Hard disk can store more data, capacity is more. And the main memory is middle between the cache and the hard disk, as far as the capacity is concerned. As far as the cost factor is concerned, cache storage would be comparatively expensive than the main memory, and the main memory would be expensive than the hard disk. So whatever device the devices at the bottom are cheaper, the device what we see at the top of the hierarchy is costlier comparatively. As far as access time means time taken to access data instruction by the CPU. How much time taken by the CPU to access the data instruction. So as far as the access time is concerned, it would be less with the cache storage. Why? Because the access speed is more. Since it is near to the CPU, the time taken by the CPU to access the data instruction would be less. And comparatively, the access time would be more in the main memory when it is compared with the cache storage. So the time, as the access time would be less with the cache storage, okay, than the main memory. So any data instruction uh, that are needed by the CPU has to be transferred into the main memory, and frequently accessed data instructions would be cached in the cache storage device. So the CPU can reference the data directly from the CPU or from the cache storage device. So any program, when they have to be executed, they have to be loaded into the memory. So when they are loaded into the memory, some space in the memory has to be allocated to these processes. So next topic what we are going to discuss is address binding. So any process, if they start the execution, they have to be loaded into the memory, because the CPU can reference the data instructions only from the memory or from the cache storage. So when the process is loaded into the memory, the data and instruction in the uh, process has to get some address, has to be assigned some address. So this is called address binding. As far as the let me explain what is address binding with a simple example. So this is a C program code, source code of a C program. This program just declares three variables, and it two input values are assigned to two variables A and B, and result computes the sum of two numbers and the result is printed. Okay, so this source code has set of variables a, b, result, and also it has instructions. Okay, so when this program starts running, okay, this program has to be loaded into the memory and these variables and instructions will get addressed. This is called address binding. So the data and instruction in the memory, in the source code are addressed symbolically. So example, this A or B are symbolic address. When this program is loaded into the memory, they will get physical address. So in between the symbolic address and the physical address, there exists something called logical address, or we can call it as relocatable address. Okay, so I will discuss about that. So before that, you have to know what is the functionality of compiler, what's the functionality of linker and loader. Compiler, linker, and loader. So compiler is a software which translates the object code into which translates the source code into object code. So here this C program is a source code. Okay, just it prints a message hello. It has a header file. So this header file contains the definition for this library function puts. Now how to compile this? So I'm going to compile this code now. So this is the syntax to this is the command to compile the source code. So I have compiled. After we compile, we get set of output files. So the source code would go as an input to the compiler, and the compiler would produce object file. So no need to worry about this concept, assembly code and all. It would be confusing to you. So please ignore this point. So just understand the compiler takes the source code as the input and gives object file as the output. Now here A.C is a source code program. I have compiled this A.C and I have got set of output files. So here A.O is the object file. This is the object file. So compiler is a software which translates the source code into object code. Okay, A.O is the object code. So I can show you this file nano A.O. So this is the object code. In this object code, please understand, you can we cannot read the other contents, but however we can read this part puts. So puts is the library function. So in the object code, please, this is very important for you. Okay, just keep this in your mind. The puts method we can see in a readable format in the object file. Why? Because please understand, the code for the puts function is not yet included into this object file. So puts is a function. Okay, that function is defined in another file, in another object file. So the code for that puts function has to be incorporated into this object file. Okay, so that not yet has happened. So first thing, let's just recall the source program goes as an input to the compiler and we get our object file as the output from the compiler. Now this object file will go as an input to another software, okay, that is called linker. So object file goes as an input to the linker and the linker would produce executable file. So here this is the executable code. So this executable code is produced by the linker. So now how to execute this process? Dot slash exec. Now it is producing the output. So please students, you have to know this basic information. So it is easy for you to understand the memory management concept. So what is happening? Any source code goes as an input to the compiler and the compiler will give the object code as the output. So here as far as this example is concerned, A.O is the object code. Now this A.O is the object code that will go as an input into the linker and the linker would produce a output file that is called executable code. Okay. So this is what is explained here. The source program goes as an input to the compiler. The compiler will give the object code. Okay. So the object code will go as an input into the linker and the linker would produce the executable code. It is not mentioned here load module. Okay. So load module is nothing but executable code. So you can see here the linker software, linkage editor or linker, same. So linker can combine one or more object code into a single executable code. So like here you are seeing one object code a dot 0, sorry, a dot o, I'm sorry. A dot O. Similarly, assume there is B dot O, C dot O. So linker can combine A dot O, B dot O, C dot O into a single executable file. Now there is another software that is called loader. So what the loader will do, it will take the executable code, what you are seeing here. This is the executable code. So loader will take this executable code and load it into the memory. It will load that executable code into the memory. So once the executable code is loaded into the memory, the data and instructions in the executable code will get physical address. Okay. So loader is a program which would load the executable code into the memory. Okay. So when compile when the compiler is compiling, that is called compile time. When the loader is loading the executable code into the memory, it is called load time. When the program starts the execution, that is called run time. Now, so what is address binding? That we have to discuss now. Binding of instruction and data to the memory address is nothing but address binding. So we have data and we have instruction in the program, correct? So this data and instruction should get some memory address. So this is called address binding. Now the question is, when this address binding will happen? It can happen at compile time. You know what is compile time, okay? It can happen at load time or it can happen at runtime. So this address binding can happen at compile or load or runtime. Now dynamic linking and loading. What is dynamic linking and loading? We will discuss. Okay, this is the object code. So when will the object code will come? When the source code is compiled, the compiler will produce the object code. For example, a.c is the source code file. It goes as the input to the compiler and compiler will produce a.o. It is the object code. Now in this object code, you can see uh, puts method is we can read the puts method. It's clear. Why? Because the implementation, the code for the puts method is not yet included into this object code. It is not yet included. This puts method is in another file. So whatever code is there, implementation code is there for the puts method, that has to be incorporated, or we can say it has to be added into this object code. It has not yet happened. Okay, so when this will happen, okay, it can happen at two stages. That is, it can happen at link time or load time. So when it happens at link time or load time, that is called static linking. Okay, please understand. If a program uses library functions, for example, in where I have shown the C program as an example. Even Java, we use system.out.println. It's a library method println. Then we use library methods like math.pow, math.sqrt. So we use many library methods in Java also, right? So when a program uses library methods, the code for the library method has to be added into the program source code. It has to be added into the source code. Source code, it has to be added into the object code. To be more, if I want to say very specifically, it has to be added into the object code. Okay. So when this will happen, it can happen during link time, or it can happen during runtime. You know what is link time? Link time means linker software. Linker software will combine one or more object module, okay, and it will produce executable code. Clear? And this linker not only combine different object modules, please also understand, it will also combine the code for the library method with the object module. Okay, so for example, our this program uses this printf library function. So this library function is in this header file. So what will happen? The code for the printf has to be added with this code. So it can happen at link time or load time, or maybe sometimes when the program starts the execution, that time this linking can happen. So if the linking takes place during the link time or load time, it is called a static linking. If the linking takes place while the program is running, then it is called as dynamic linking. So what are the advantages of dynamic linking? Because dynamic linking has a lot of advantages. Number one, it saves the memory space. So dynamic linking, if dynamic linking is used, remember, more than one process can share the same library files. So more than one process, if they are running and if they are in the memory, they can share the same library files, and it is enough that the system loads these library files only one time in the memory. No need to have separate copy for each and every process. So all the process which are running, they will share the same library file. So it will save the memory space. And also there is no need to, if more than one process share the same library files, no need to load these library files many times. It is enough that one time it is loaded, all the process which require these library files, they would share. So saving the library files into the memory also, uh, saving time also reduced. And also these library files can be easily updated using the dynamic linking concept. Suppose if there is a bug in any library files, it can be the update can fix the bug, and whatever update happens, that would be immediately visible to the processes. Since the processes they link to these library files only during the execution, whatever update happens, that would be immediately available to the processes. So this is the third point, ease of updating the libraries. Next is what is meant by logical and physical address. So just again come back. The source code, when you compile, you get the object code, and the object code goes as an input to the linker, and the linker produce executable code. Now this executable code, so this is the executable code. So this is executable code. So in this executable code, all the code for the library functions are incorporated. So the data and instructions have some address in this executable file. Okay, there are addresses for each and every data and instructions. So the address of data and instructions within the executable code, executable file, is called logical address. Okay, please understand. So this is the executable file which I have opened. So in this file, data and instructions, they have some address. Okay, they have some offset value. That is called logical address. So this address is valid only within this file. It is not valid outside this file. Okay, so this address is not related to the memory RAM, memory device. Please understand. This is specific to this executable file. So a logical address is one referred to in a piece of executable code. So you know very clearly now what is executable code. The address of data and instruction within the executable code is called logical address. Okay. Um, the CPU, please understand, when a program is running, okay, so the CPU might need the data instructions. So it would request data instructions. So when it requests a data instructions, the CPU will use only the logical address. It will not use a physical address. It is very, very important. The CPU, when it references data instructions for a specific process, it will use the logical address. Okay. Then what is the physical address? The address of data instruction in the memory device, like random access memory, main memory. So in the main memory, when the executable code is loaded, the data and instructions, they will get some address, correct? That address is called the physical address. So the logical address space, okay, what is the logical address space means? The logical address space can extend from 0 to the memory limit of the process. So it depends on the size of the process. Process means the program which is running. So if the process is big, the logical address space will be more. If the process is very small, the logical address space will be small. Okay, so it depends on the size of the running process. Whereas the physical address is related to the memory device. So the physical address space is related to the size of the main memory device. Okay, so these are the important points about the logical and physical address. Next one is what is meant by memory management unit. Before I go into this topic, I have skipped this slide before, so let us revisit this particular slide. So any process in uh, uh, which are running, which are loaded into the main memory and which are running, the operating system would maintain two informations. One is, for each and every process, there is something called base address value and limit register value. So what is a base address means? In the memory, for example, let us say this is process P0. Okay, this process P0. Let us say this is process P1. Let us say this is process 2, P0, P1, P2. Just assume. Okay. Now this process P0 starting address is 25 256,000. Okay, this is the starting address, and it's the process 2 starting address is this. Okay, 340, this one. Okay, this is the starting address of the second process, and this is the starting address of this process. Okay, so let's say for the process P1, this is the base register value. Okay, so this is in the memory. This process address space starts from this area. Okay, base register value. And what is the length? How much space it is using in the memory, that is determined by the limit register value. So this is the limit register value for this process. So when the CPU is asking any instruction or data, that address of that instruction or data should be within this address. Within this address. For example, this is process P1. Now this process P1 is running. Okay, so for this process P1, let me do a simple exercise. So process P1, what is the base register value? So 300, 0. So this is the base register value. What is the limit register value? Okay, so this is the limit register value. Let us say the CPU, okay, is running the process P1. The process P1 is running with the CPU. And the CPU, while it is executing the process P1, it is asking some data or instruction for this process P1, and it is giving address. Actually, it uses a logical address. Please understand, it uses logical address. So it wants some data or instruction in this address. Okay, so the process P1 is running with the CPU. The CPU is asking, okay, give me some data instruction in this particular address location. So the operating system would compare this address, this is logical address. Okay, this logical address for the process P1. It will compare this address with the limit register value of this P1. Is it less than? Is it less than the limit register value? Yes. Yes, true. Okay, true. That means, okay, please understand, uh, the process one is accessing some data or instruction within its address space. That is, it is not accessing any data instruction belonging to another process. It is accessing its own data instruction. Okay, then please understand, 120,800 is the address. Okay, plus what is the base register value. So when you add this, you will get something that is called physical address. So this is the physical address value. So what you understood, please students, for each and every process, the operating system maintains two things. One is base register value, another one is limit register value. Okay, so whenever the process is running, when the CPU references any data instruction in a specific address location, the CPU would give the address, logical address. Okay, it will tell, okay, please, this is the logical address. In this logical address, please give me data instruction. So system would compare this logical address with the limit register value. Always this logical address should be less than the limit register value. It should not be more than. Okay, it should be less than or equal to this value. Okay, just a minute. You can see the diagram here. Sorry, it should be less than the limit register value. Okay, then once it is confirmed that the logical address is less than the limit register value, it is combined with the base register value, and then you will get the physical address value. So this is the point what is discussed here. So every process has base register and limit register value. So we are now in the position to discuss the memory management unit. So in this slide number 9, we discussed what is a logical and physical address. Okay. So the CPU always uses the logical address. So when the CPU is asking some data instruction, it will give the logical address. Now the system has to convert this logical address into physical address. Okay, so memory management unit is a device in the system. The functionality of the MMU is this: it would translate the logical address into physical address. Very simple. Okay, so when the logical address is given to the MMU, okay, it will find the corresponding physical address. So how it is doing this calculation, already we have discussed. The CPU, when it is executing any process, it will give the logical address. Okay, already we have discussed this, remember, in this example. So it will give the logical address. So uh, memory management unit, what it will do, it will compare that logical address with the limit register value. Each and every process, they have base register value and limit register value. Okay, base register value and limit register value. So it will compare the logical address with the limit register value, and the logical address should be less than the limit register value, less than. So in this example, the logical address value, is it less than the limit register value? Yes, true. So if it is true, yes, then what will happen? The logical address will be added with the relocation register value. Relocation register value is nothing but a base register value. So I have said already, base register value, or also we can call this as relocation register value. Okay, so both are same. So please again recall students, I am explaining how logical address is computed, mapped into physical address. Okay, so CPU would produce logical address, it would give logical address. That logical address is compared with the limit register value of a process. The logical address should be less than the limit register value. Okay, So if it is less than the limit register value, then the address mapping would proceed. The logical address will be combined with the base register value or relocation register value. Then the result is physical address. Suppose, please understand, if the logical address is greater than the limit register value, if it is not less than the limit register value, then what is happening is it is a trap. Okay, what is a trap means? It's an error condition. That is a process, let's say P0 is trying to P1 is trying to access another process memory. This process P1 is trying, if it tries to access any data instruction from another another process location, then that condition is called trap. That would be shown using error condition. Okay, we can call it as trap. So this is what we are discussing. What is a memory management unit? It is a hardware unit in the system that maps the logical address into physical address. So how it is happening? When the CPU gives the logical address, that logical address is added with the relocation register value, and or we can call it as base register value. Then what we get is the physical address. Very simple. Uh, Before we go into this, let us complete this concept. So how memory allocation and protection is how the protection is implemented in the operating system. So the point is this: how a process is not allowed to access another process memory location. So just come back here. Let's say this is process 1. This process 1 cannot access any data instruction from another process location. Okay, how the operating system is implementing this protection? Okay, so explain with a neat diagram. Very simple. When the CPU is running a specific process, let's say P1, okay, for that process 1, the CPU might need some data instruction from a specific location. So CPU would give the logical address. Then the logical address is compared with the limit register value. Okay, if it is less than, it will be added with the base register and physical address is calculated. Otherwise, error condition will be happening. Okay, so this is how the memory protection mechanism is implemented by the operating system. So far, students, as a first part, let me recall what I have covered. We have discussed about the different memory devices and their characteristics. Then we have discussed about the process base register value, or we can call it as relocation register value and limit register value. We have discussed about address binding. The address binding can take place at different time: compile time, load time, and run time. Then please recall, these basic things like what is a compiler doing, what is a linker, what is a loader, and what is dynamic linking and loading. Okay, what are the advantages of dynamic linking and loading, and what is meant by logical and physical address, briefly explain. So what is MMU, explain. Okay, support your explanation with a diagram. Then how operating system protects the memory uh, from invalid memory access. So explain with a diagram, show. Okay, so these are the basic things we have covered in the first part of the memory management. We will continue other topics in the second part. Thank you very much.
So in this session we are going to discuss about the concept of swapping. In swapping, when there is a limited memory space, some processes from the main memory would be swapped out to the swap space in the secondary storage device. And when the space becomes free again, then that process would be brought back, swapped in back to the memory space, to the main memory from the secondary storage. So this concept is called as swapping. Swapping is done by the module in the kernel named memory manager, and this memory manager has to work in synchronization with the CPU scheduler, which you have studied in the chapter 4, like round robin scheduling algorithm, FCFS, then priority based scheduling algorithm. I can give one simple example. When the amount of space in the main memory is less, and assume there is a process running with low priority, then a new process has to be loaded into the main memory, but there is no enough space in the memory. So the process which is currently running with low priority would be swapped out to the swap space in the secondary storage, and the space would be allocated to the process with high priority. So when the high priority process finishes its task, when it terminates, the process which was swapped out to the secondary storage with lesser priority, that process would be swapped in back into the memory. So this is a typical example for swapping concept. The swapping is implemented using a swap file in the Windows operating system. We can access this file here: properties, advanced system settings, performance sorry, here. So here this is a virtual memory file. So the current size of this virtual memory file is 2432 MB. If we want, we can change the size of the file. So as far as the Windows operating system is concerned, the swap file is implemented, the swap space is implemented as a file. As far as the Linux operating system is concerned, we can implement the swap space either as a file or as a partition. So if you want to see the swap space in the Linux operating system, the command is swap on and summary. So here you can see this partition is allocated for swap space, and its space is given here. And also in the Linux operating system, we have the provision to implement the swap space as a file. In this part, we are going to discuss about the memory allocation technique. The memory allocation technique can be classified into two types: contiguous and non-contiguous. Once again, the contiguous technique can be classified into simple and complex. Let us see what is the difference between the contiguous and non-contiguous memory allocation technique. So let us assume this is a memory space, main memory. So in this main memory, let us load a process. Let us assume a process is loaded, process 1 is loaded. The process 1, if it gets the space contiguously in the memory, then this is called contiguous memory allocation. So the process 1 is stored in the memory, okay, at the same place. Whereas here in the non-contiguous memory allocation technique, example segmentation and paging, which we will discuss later, the process would be split into different parts, and each part would be stored in different places of the memory space. So this technique is called non-contiguous memory allocation technique. So now once again, the contiguous memory allocation technique, which we have discussed here, okay, can be classified into two types. One is simple, another one is complex. Under the simple memory allocation technique, the full memory would be first of all divided into user space memory and kernel operating system memory space. and the user space memory would be split into equal parts. Let us say we have the memory has 400k space, that would be equally split into 4 parts. Okay, and the process would be, whenever any process requires memory space, then the process would be loaded, the process would get equal amount of memory space. So for example, the process 1 whose size is 80k is stored in the first hole, and since the memory process P1's size is just 80k, it is wasting 20k of space. So this 20k space which is wasted cannot be used by the other process, and hence this problem is called internal fragmentation. So when a process gets more space than what it requires, then under the simple memory allocation technique, it would result in a problem called internal fragmentation. Now another part of this memory is occupied by the process 2. Its size is 100k, let us assume. So here no space is wasted. Then the third part is consumed by the process 3. The process 3 size is just 50k, so it is wasting 50k space, and this space is not usable to other processes in the system. Hence it is also suffering from internal, it is resulting in a problem called internal fragmentation. The second technique, way of contiguous memory allocation technique, is called complex memory allocation technique. So in this technique, the memory would be split into different parts of various sizes, different sizes. So let us say in this memory we have a space of 100k, 50k, 150k, 200k and 300k. So these free spaces, different free spaces of varying sizes, are called as free holes. So let us say a process P1 needs 190k sorry, let us remove this. A process P1 needs a memory space of 190k. So here this free hole would be suitable for this process P1. So the system would allocate this free hole to the process P1. So in that 190k is used from 200k by the process P1. So when the process P1 is stored in this free hole, it would result in a leftover hole free space of 10k. So now this 10k is available to other processes. Okay, so whenever any process is stored, whatever space not used, that would be considered as leftover hole. Here this technique can suffer from a problem called the external fragmentation. So what is external fragmentation? Let us say this process 2 So process 2 needs a memory space of 310k. So here we have 310k space, 150 plus 50, 200 plus 100, 300 and 10k is here. But however, this free spaces in the memory is not together, contiguous. Under this technique, remember, a process needs the memory space contiguously together in the memory. Since the process 2 needs a memory space together in the memory contiguously, whereas in the memory, the free space, required free space is not contiguous, then because of that, process 2 cannot be loaded into the memory. Why? Because 300k space is together, existing together, but 10k is in another part of the memory. Hence the process 2 cannot be loaded into the memory. Even though there are free spaces, still the process 2 cannot be loaded since the free spaces are not together. This problem is called as external fragmentation. So please recall, the simple memory allocation technique suffers from a problem called internal fragmentation, and the complex memory allocation technique under the contiguous memory allocation suffers from the external fragmentation problem. So this is what discussed in these slides. So what are the internal and external fragmentation? External fragmentation, if memory is broken into many holes, there might be enough memory in the total to fit to a process, but all these blocks are not together, all these holes are not together, not all in one place. So here there are two free spaces. Even though there are two free spaces, the P1, since the P1 is very big, even though the P1 can be stored using the combined free spaces of the of the holes, existing holes, since they are not together, the process P1 cannot be loaded into the memory. So this problem is called external fragmentation. So what is internal fragmentation? When a process is allocated more space than what it needs and the space not being used. So this is internal fragmentation. Okay, so here 20K space is wasted and this space is not available to other processes. So these are the two drawbacks of a contiguous memory allocation technique. So here we have to discuss some algorithms which is used by the system to choose a hole. These algorithms are first fit, best fit and worst fit. So let us discuss this algorithm with a tutorial problem. So here let us assume there are three processes, process P1, P2 and P3, and these are the free holes that exist in a memory device of different sizes. Now the process P1 needs a memory space of 8K, process 2 needs a memory space of 20K, process 3 needs a memory space of 28K. So there are different holes of different sizes available in the memory. Now which hole has to be selected for each and every process? Okay, to decide that, okay, system can use any one of these three algorithms, best fit or first fit or worst fit. Let us go to the worst fit algorithm first. So according to the worst fit algorithm, the biggest hole available in the memory would be selected for the processes. So for the process P1, 8K, okay, it needs 8K. Which is the biggest process available? 40K. So 40K would be selected for the process P1. So you can see process P1 is stored in the hole of size 40K. So when the process P1 is stored in the hole of size 40K, it consumes only 8K space. So it would result in a leftover hole of 32K. Once again, this is not internal fragmentation. This is available. The 32K is available for other processes. Okay, it is not internal fragmentation. Please understand, this is available for other processes. So other processes can be stored in this free leftover space. Now, so after process 1 is stored here, what are the remaining spaces available? 34K is available, 6K is available, 18K is available, then 32K is available, and 14K is available, 22K is available, and 32K is available. Now second process P2 needs 20K. So for 20K, the worst fit algorithm would analyze each and every hole available in the memory. So which is the biggest hole available now? The second biggest hole available now is 34K. Here there is 32K available here, and also here 32K is available. Okay, but 34K, since 34K is bigger than these two holes, for the process 2, this hole would be selected. So process 2 would be allocated from the 34K free hole space, and it would result in 14K leftover hole space. So now we have 14K also available, okay, for other processes. So P2 is stored here. So now after allocating space for the P1 and P2, what are the remaining holes? 14K is available, 6K is available, 18K is available, 32K is available, 14 is available, 22 is available, and 32 is available. Now the third process is process 3 needs 28K. So the worst fit algorithm will analyze the holes from the beginning. Okay, so here the 14K is not enough, 6K is not enough, 18K is not enough, then we have here 32K. So in the 32K, process 3 can be stored. So process 3 whose size is 28K is stored in this hole, and after storing the process 3, it would result in a leftover hole space of 4K. So this is the free space now. So now all the three processes are stored according to the worst fit algorithm. Next algorithm we are going to discuss is first fit. So according to the first fit, this algorithm would search the holes from the beginning. So whenever it finds the hole which is big enough, that hole would be selected. So now for the process 1 needs 8K. So it would analyze the first hole. The first hole size is 34K. So the process 1 can be stored in this first hole itself. It will not search all the holes. It won't analyze all the holes. It would whenever it finds the big hole, whenever it finds a hole which is big enough, then that hole would be selected. So process 1 would be stored here in this hole. Process 1 size is 8K. So 34 minus 8, 26. So 26 is the resultant leftover hole. So it is free now, and this can be used this can be allocated to other processes. Now the process 2 needs 20K. So this algorithm once again starts from the beginning. It would analyze the first available hole. The first available hole is 26K, whereas the process 2 needs just 20K. So for the process 2, from 26K, 20K is allocated. So it would result in the leftover hole of 6K. So process 1 also allocated, process 2 also allocated. Now process 3 needs 28K. For process 3, the first fit algorithm would start from the beginning. It would analyze the first hole. 6K is not enough. Then it would analyze the second hole. This is also not enough. Then it would analyze the third one, not enough. And the third hole, which is 40K, is enough for the process 3. So process 3 is stored in this space. So when it is stored, process 3 size is 28K, and it would result in leftover hole of 12K. So this is the first fit algorithm. Now the third one is best fit algorithm. So best fit algorithm would analyze each and every hole, and it would find the smallest hole which is big enough. So the main objective of the best fit algorithm is it has to select a hole in such a manner that the resultant leftover hole is small. So for the process P1, This is very big. So if process 1 is stored here, the resultant leftover hole would be very big. Then this hole cannot be used for the process 1. Then this is also quite bigger. This is also very big, and this one is small but big enough to store the P1. So to store the process 1, this hole is selected, and the leftover hole would be 6K. Then process 2 is stored in the second one. It would result in the leftover hole of this. So process 3 would be stored in this hole, 32K hole, and it would result in the leftover hole of 4K. So this is what you have to know about these algorithms: best fit, first fit and worst fit algorithms. So first fit algorithm allocate the first hole which is big enough. Best fit algorithm finds a hole that leaves the smallest leftover hole. Worst fit algorithm finds the hole that leaves the biggest leftover hole. So whichever hole is very big, that hole would be selected for the processes. So when we compare these algorithms, what are the advantages and disadvantages? First fit algorithm is quick, but it would result in it will not give the optimal solution, because it might result in a big leftover hole, whereas the best fit algorithm has to analyze each and every hole which are available in the memory. So exhaustive search, whereas here there is no exhaustive search. Whenever a big enough hole is found, the search would be stopped and that hole would be allocated. So whereas the best fit algorithm, each and every hole available would be analyzed, and the resultant leftover hole would be small. Here also same like best fit algorithm, each and every hole, the worst fit algorithm also, in this algorithm each and every hole has to be analyzed. It would result in a large leftover hole. So already we have discussed this internal and external fragmentation. Next topic what we are going to discuss is non-contiguous memory allocation. So in this we are going to discuss about the paging and segmentation. Now we are going to discuss about the non-contiguous memory allocation technique. In the non-contiguous memory allocation technique, process would be split into different parts, and these parts of the processes are stored in different locations of your memory. The technique, non-contiguous memory allocation technique, what we are going to discuss today are paging and segmentation. So what is a paging? Paging is a non-contiguous memory allocation technique. So in the paging technique, a process logical address space is divided into pages. So a single process would be split into multiple pages, and the physical memory would be logically divided into frames. So this is the process. The process is split into pages, and the main memory would be split into frames. So that you can see in this slide. So this slide shows the concept of paging. So a process is split into 4 pages, page 0 to page 3, and the memory is split into 7 frames, frame 0 to frame 6. So each and every frame in the memory would be numbered. Okay. So now this page 0 is stored in the frame 1, page 1 is stored in frame number 4, page 2 is stored in frame number 3, and page 3 is stored in frame number 6. So pages belonging to a process are stored non-contiguously in different places of the memory. So here this technique would eliminate the external fragmentation. External fragmentation would come when the memory allocation technique requires the process to be allocated a contiguous memory allocation. So here this paging is a non-contiguous memory allocation technique. Now when the pages are stored in a memory in different frames, okay, so the frame in which a particular page is stored, that has to be entered in the page table. So this table contains the entry of page number and frame number and valid invalid bit. So this table indicates that page 0 is loaded into the frame number 1, and since the page is available in the memory, the valid or invalid bit here indicates valid. The page number 1 is loaded just a minute, there is a small confusion. So page 1 is loaded in the frame number 4, and page 2 is loaded in the frame number 3, and page 3 is loaded in the frame number 6. So now when the CPU, as far as the paging technique is concerned, when the CPU gives a logical address, already we have discussed this point, that the CPU, when it wants some data or instruction, when it is executing a process, it would request the data instruction using the logical address. So what is the logical address? It is the address of data and instruction within a executable file. Now this logical address under the paging technique has two parts. This logical address has two parts. The first part of the logical address is the page number, and the second part of the logical address is offset value. So the first part is called page number, second part is offset value. So when a CPU wants data instruction from a specific location, it uses the logical address. So from the logical address we will get the page number. From the page number, the paging system would look for the frame number in the paging table. So it would obtain the page number from the paging table, then that frame number is added with the offset value, that would generate the physical address. So from that physical address, the data instruction would be fetched and given to the CPU. So what else we have to discuss? So as far as the paging technique is concerned, there is no external fragmentation. However, there is internal fragmentation. Already we have discussed this in the previous section. And the paging enables the swapping technique. It makes a swapping technique easy to implement. However, the memory access time increases when paging technique is used, because additionally the paging system has to find the frame number for each and every page value in the logical address in the paging table. So the access time also increases, and moreover a paging table has to be maintained for each and every process in the main memory. So extra memory space is needed to support the paging table. So let us discuss some basic questions about the paging system. The external fragmentation, there is no external fragmentation as far as the paging technique is concerned. However, internal fragmentation is there in the paging technique. How big the page size should be? It should not be too small. Okay, it should be of medium size. Then how many page tables do we need? For each and every process, a separate page table is needed. So one for each process. How does the operating system keep track of a process page table? I think we studied this in chapter 2 or 3. The process control block is a structure which stores the information about a process, like code section, data section, process tag, memory information, accounting information. So all these informations are stored about a process in the process control block. So the paging table information also stored in the process control block. So this is what I want to discuss about the paging technique. Let us discuss a simple example now. Now let us work out a tutorial problem in the paging concept. So given a set of pages and frames and a paging table that maps the page number into the corresponding frame number, we have to calculate the physical address from the logical address. Given the logical address, okay, we have to find the page number, offset value, and the physical address. Let us assume that 3 bits belong to the logical address and 1 bit, okay, belongs to the offset value. So from this given logical address, the first 3 bits belongs to the page number and the last bit belongs to the offset value. So in the paging table, for the page number 000, we can find the frame number, corresponding frame number. The corresponding frame number is 111. So when we add the frame number with the offset value, we get the physical address. So this particular page is stored in this particular frame number. So this page is stored in this frame. So second one, let's say this is the given logical address. So from this we obtain the page number. The last bit, least significant bit, is the offset value. So for this page number we obtain the frame number. Since the page is present in the frame, okay, we can see the valid bit here. Then when we add the frame number and the offset value, we get the physical address. Whereas this logical address raised by the CPU, okay, so the page number is this, the offset is this, but we don't have any frame entry for this particular page number in the paging table. So it is invalid access. A page fault occurs. So when a page fault occurs, the operating system has to find whether it is a invalid memory access or a page fault. If it is invalid memory access, the process would be terminated. Otherwise, if page fault, that is the page not found in the process is trying to access its own page, and the page if not found in the memory, then the page would be loaded into the memory by the system, operating system. So that we will discuss, that topic will discuss in the chapter number 8. So this is what I want to tell about the concept of paging. Now we are going to discuss about another non-contiguous memory allocation technique called as segmentation. In the paging scheme, it is a hardware, the paging hardware, that partitions a CPU generated address into pages. So process address space is split into pages by a paging hardware. But in the case of segmentation, when the process is getting compiled, at that time the process components are divided or split into segments. For example, this is the logical address space of a process. So the main function, stack, and the library methods. So each component of a process represents a separate segment in the segmentation technique, and these segments, they will have a number, identification number, segmentation number. So when a CPU is requesting some data or instruction for a specific process, its logical address would be representing a segment number and offset value. In the case of paging technique, the logical address would be representing a page number and offset value. In the case of segmentation, it is segment number and offset value. So the segmentation technique has to map the logical address into the appropriate physical address. For that, a segmentation table is supported by the segmentation technique that would allow the logical address to be mapped into the appropriate physical address. So let us discuss that with a simple example. So these are the segments. Just now I told that when a process is split into segments, each and every segment would be identified by a number, and each and every segment has a base value and the limit register value, that is the length value, how much space it is occupying in the memory. So what is the starting address and how much length it is, how much space it is occupying in the memory, that would be indicated, determined by the length value. So segment 0, starting address is 1400 in the memory and its length is 100. Suppose the CPU wants to read some data, access some data or instruction from this particular logical address. So already I have said the logical address in the segmentation technique represents the segmentation number and the offset value. So this first value is the segmentation number 2. So the second value is the offset value. So for the segmentation number 2, this is the base address. So this is a starting address in the memory, okay, and its length value is 500. From starting from 900, it will outreach until 900 plus 500, so 1400. So here the given logical address, okay, the offset value is 70. So it is, when we compare this offset value with the length of the segment, it is less than the length. The offset value is less than the length. So the process is trying to access its own memory space. It is not trying to access another process address space. So segmentation number for 2, the offset value is 70. Is the offset value 70, is it less than the length value 500? Yes, true. So now when the offset value is combined with the base value, okay, 900 plus 70, 970, this is the physical address. So in this location, okay, okay, the CPU can access the data or instruction for this particular logical address. Let us work out the second logical address now. Now here the segmentation number is 4, the offset value is 100. For the segmentation 4, the length value is just 10. However, here in the logical address, the offset value is 100, which is less than which is more than the length value for this particular segmentation. So since it is more than since this offset value is greater than the length value, then it is an invalid memory access. So the process is trying to access, another process memory space. So similarly, now let's work out the third logical address. Here segmentation number is 3. For that, the base starting address value is 200 and its length value is 700. Here the offset value is just 500. It is less than the length value. So the offset value is added with the base value to obtain the physical address. So this is how the segmentation technique works. Now let us discuss the advantages and the disadvantages of the segmentation technique. So in the segmentation technique, no internal fragmentation, that is advantage of this technique, whereas in the case of paging we have the internal fragmentation problem. However, the external fragmentation problem reoccurs in the segmentation technique, whereas the external fragmentation was not there in the paging technique. Then in the segmentation technique, for a particular process, many segments would be created. The process would be split into many segments. So for each and every segment, different protection mechanism can be configured, like read write permissions. So for the segment 0 only, it is read only format. Here in this example, for the segment 1 can be readable and writable. So this protective mechanism can be configured for the segments. How to configure this protective mechanism is beyond the scope of our lecture, so I am not going to discuss that in depth. Then it is very difficult because here the segment, each and every segment need the memory space contiguously. So it is difficult to allocate a contiguous memory space to the each and every segments because of external fragmentation problem. So these are the disadvantages of the segmentation technique. So with this I conclude the lecture 7 about the memory management. So next chapter we will discuss about the virtual memory concept. Thank you very much.